program Knossos that we've used for EM, but Partha also showed can be used for LM. And this is now a data set, again from the mouse retina, but it does contain intracellular staining, and I just want to make you familiar with that just very briefly. And now this is finally really tutorial style. So why don't we try to find out what we can see in such data. So first of all, these are the 3 orthogonal viewports that I told you about. Do you have a pointer? Just a laser pointer, that would be ideal. Thank you so much. Okay, perfect. So this is the XY viewport. That is the viewport, the plane in which the data was taken. And these are the orthogonal reslices. So this is the entire data cube. The images were taken with the EM from the top of the block, but then assembled, right? Okay, now the question is, does any of this make sense to any of you? And we're going to play a game that goes like this. I point at something, and you tell me what you think it is. So, for instance, this thing here, is it visible on the screen? Can anybody orient at all yet? Because what we'll do now is, I promise you, within 30 to 60 seconds, you'll be what we call experts at EM data annotation, and that will be a proof of the performance of your visual systems, okay? So we can agree that you didn't see anything right now, right? Okay, so now we're going to get there. So this is a mitochondrion, okay? Have you seen mitochondrion in textbooks? Yeah. So they are small and kind of ellipsoid. In the brain, they are very complex, long, weird, and because we don't care about them, we don't like them, right? So for circuit reconstruction, we don't want to know about mitochondria, but for instance, this is one. And this entire elongated thing is a mitochondrion. This is the reslice of that one. So they can be really longish, and they sometimes even branch. They're really weird in the brain. So for instance, this one is running for a very long time here. I can see that in the bottom plane. So again, black, weird mitochondrion. So the rule in that kind of data is that anything that looks weird is a mitochondrion, okay? So this is really important to realize. So what is this? Mitochondrion. Take those ugly black things here, 3 mitochondria. 1, 2, 3. I mean, this tells you something about the brain. It's a pretty energy-consuming thing, right? Because that's what mitochondria are there for, and we know that. By the way, what is using the energy in the brain mostly? Where does it go mostly? Anybody? Just to link it back, where is the energy actually consumed that the mitochondria produce? Mostly, at least, the largest. Yeah, but what exactly? I mean, what ATP? Yeah, it is ATP, but which ATPase uses most of the energy in the brain? It's the sodium-potassium ATPase that returns over kind of the sodium-potassium gradient that's running all the time. So that's where the energy goes, right? Sodium, potassium ATPase, and that's what these mitochondria are there for, to fuel it. Okay, now again, mitochondria, ugly here, mitochondria. There's only one other structure that I'm going to show to you, which is, we talked about the brain being there to transmit signals, and it does so largely also by chemical synapses, and chemical synapses need vesicles. That's where the transmitters are. So I'm now going to introduce you to vesicles, if you haven't seen them before. So these small dots here are vesicles, and you can see them here also. These are synaptic vesicles. The contrast on the screen is not optimal, but all I have to do is move it around a little bit, and I think you'll agree that there's the red plane is focused right now at something that contains a lot of red vesicles. Do you agree with that?
Why do I get an illusion that there are vesicles in the mitochondria?
Okay, what do mitochondria contain? The textbook picture, and that is not so wrong, is what is called crista. It's these membranes.
Yeah, it doesn't look like.
Well, if you look at the reslice here, you see that they are actually elongated. So it's really, one has to be careful about the 3D. That's why we think the 3D is so important, because you really want to have a 3D picture. And what is, let's say, a kind of longish thing can, in a reslice, look like almost a vesicle. It's not, but it can. And the other thing that can be there are microtubules, which also can look like a vesicle in a reslice. For instance, here, this particular process here contains those two dots, which are not vesicles, but I think at least, but are more likely to be to run for a little bit longer time, as they do here, and maybe microtubules. So okay, so there's a lot of small stuff, but the only reason I'm showing you the small stuff is that you can get rid of it visually. Because now we want to look at a process, and I'm going to show you one now. So this thing here in the middle is a neurite, and we can see it run away. So here, can you all see this thing that I'm looking at here with the mouse there? This is a neurite, okay? And it's probably a dendrite because it doesn't contain vesicles, but other weird stuff, but not like a mitochondrium, which is ugly. But okay, can you see that there still is that doable? Okay. I will going to choose another one just for comparison, so that you. So again, mitochondrium here, mitochondrium there, ugly, but it is within a neurite that in this reslice here can be seen, and then you can walk through it and. Like this, and try to follow it. Okay? Here, you see it? Okay. The reason I'm doing this is because I think by now you're all able to do it. Yeah? And we'll try this now. So who thinks he has seen enough of EM data to follow a neurite? Just a little bit. So we'll have a little, just as the end of this whole thing, a small competition. We're going to start at the neurite. So again, this is an easier one. In this blue window here, this is the circumference of a neurite. Can you see this? And then if you move along, then it's traveling. Is that visible? I think so, right? So now the task is to follow this neurite here, and there's a speed accuracy trade-off, so you can go faster if you want, but if you miss a branch point, we'll all make fun of that. And so that's what I want to invite you to. So who thinks he can follow a neurite? Or who thinks at least one should try? Or who's at least competitive enough to try it? It's like a game. Come on. Is it, usually it's not. Yeah, see. Okay, very good. Okay, so all you have to, so you look at this window. Yeah. You press F for forward, D for backward. Just put your two fingers there, and then you can use the mouse to steer. Okay. And just go on this axis. It's mainly going to run on this axis. And if you want faster, tell me. So I'll of course take your time. So at some point there will be a black plane that tells you that you're done. Okay. And then we'll time you. So this is a stopwatch. Okay, so ready, steady, go. Okay, and everybody follows this right window up there. Can you see it? And he's very nicely following the right. Ugly mito in view, but no problem because he's still oriented. Very good. Now the neurite starts traveling, as you can see, right? Oh, too fast. Yeah, whatever. Take your time if you need it, but it is competitive.
Am I still there?
Yeah, very good. Very good. Oh, you have to use your mouse in the upper window, ideally. That makes it easier. Sure. Yeah, just go on.
Okay, so here.
Yeah. Very good. Very good. So you're traveling through the retina right now along, actually, excellent.
Got a bit lost.
No, just you're still doing it well. Very good. Further, further. You can see all the stuff that's happening around it, also exciting, but we want to focus on this particular neurite. I think recenter your mouse would help, I think, if you stop it. Yeah. Okay, very good. Very good. Yeah, stick with it. And movement helps, as you can see, right? When it's still, it's much more difficult to understand, but if it's moving, it helps a lot. So our brains are very good at extracting or integrating information over moving or changing but correlated images. So that is also something that you can see here clearly. Still in it, very good. Now careful, careful. Mitos in view, yeah. Go on, go on. Time is still running. Yeah, now it gets really wow, right?
Whoa.
Very big. So this is an axon terminal, as you can see, many vesicles, and it's making synapses all over the place. Stick with it, stick with it, stick. Yes, stick with it. Go, go, go. And blank, done. Very good, very good, very good. So the reference is 1 minute 50 for that particular axon. So I'm now going to reposition you on that axon. Who wants to take up the challenge? First of all, bravo. I mean, this is really a 30-second tutorial on how to fly through the brain, and you got it. Very good. So I'm pretty sure the organizers will have a present for you or something like that. Yeah, but that's actually our experience, that it takes so little. And first of all, we have to really congratulate, I think, evolution on our brains, right? Because what we did was solve this problem. You know, first you saw nothing, and then all we did, we moved the images, we showed you what mitochondria are, and basically you were done.
Is there any approach to use it as a video game like they did for the borderline folding and stuff like that, and put it online so that
Yeah, so this is exactly what my group is working on right now. So we're building a browser-based game around this, because out of this experience. First of all, you can turn it into kind of fun, at least a competition, and that always helps. And secondly, it's so intuitive if you put the data in the right way and if you tell people the right things. So yeah, we're doing that right now. The hope is really to scale up that kind of annotation by some orders of magnitude. Okay, so just a competitor, I think we need at least one comparison run. Who thinks you're better? Okay, good. Okay, and I'll give you something that I didn't give you, which is unfair. I'll show you the speed up button. If you think it's too slow, and then we can see whether that helps.
we should compete on the same speed though.
Okay. It's really serious. Okay, good. Then we'll do that. Okay, but if you're desperate, you can just go on, plus, and then it's twice the speed. Okay.
So which are the controls?
So the controls are F, right here. F forward, T backward, and the mouse to move. Okay. So ready, steady, go.
Sorry. Okay, I cheated there.
So do you want to speed up?
Yeah.
Okay. Okay, so for all of us, this is the second time we see it, and the factor of 2 is not a problem, as you can see. Yeah. So before we were struggling with speed 1, but actually you could think this is even easier because
More movement. Easier to follow away.
Yeah, you're doing a great job. You're very good. Very good.
For the mitochondria there.
Yeah.
Which one?
Yeah.
This one.
See, that was a minute because of factor of 2. No problem. I didn't show you. No. Okay, and now you know this was not about the competition. This was about showing this effect. Bravo again. Very good. But really, so that's how complex our brains are, but how good our brains are at reconstructing our brains, and that's what we're doing. So I hope you enjoyed this a little bit. Okay, that's it.